All right, so as I gave some more thought to this, I decided we're just going to move on to 1.6, which is the trig functions. Okay, the radian measure of the angle ACB at the center of the unit circle equals the length of the arc that ACB cuts from the unit circle. The figure shows that S equals R theta, which is the length of the arc cut from a circle of radius R when the subtending angle producing the arc is measured in radians. What does all of that mean? It makes more sense whenever we have the picture. So what that says is if I'm looking at my unit circle here, which is the smaller one that had a radius R, we talked about the unit circle earlier this year, and whenever I look at this unit circle, the radius is 1, and I have a length theta, which is my actual angle measurement for ACB. So this theta, in order to find how long this arc is out here, whenever I have a longer radius, it tells me that to find that arc length S, in order to do it, all I have to do is S equals R times theta. So my angle measurement times the radius is going to give me my arc length. Now, conversions, we can go through this fairly quick because we've done this already. Since pi equals 180, converting radians and degrees, if I want to find my radians, I take the degrees times pi divided by 180. So that's 90 pi over 180, which is pi over 2. 135 times pi over 180. 135 over 180 is going to reduce to is it 5 over 6? 5 pi over 6? See, 45 goes into both of these. That's going to be 4. It's 3 pi over 4. Yeah, I know, I'm a genius. To convert to degrees from radians, we do 180 over pi. So I'm just going to take my radian measure times 180 over pi. Pi over 6 times 180 over pi. Pi's cancel. 180 divided by 6 is 30. 3 pi over 2. Same thing. Pi's cancel. 180 divided by 2 is 90. 90 times 3 is 270. Again, we just did these not too long ago. An angle is said to be in standard position if its vertex lies at the origin and its initial ray lies along the positive x-axis. Angles are measured counterclockwise from positive x-axis. Those are positive measures. And remember, if we go clockwise, it gives us a negative angle measurement. Remember that our measurements can go beyond 2 pi radians or 360 degrees, and that's also true for negative angle measurements. I can go around more than once and further than one distance, one circle. From here on out, we will use almost exclusively radian measurements unless otherwise stated. So degrees kind of disappear now. 6 basic trig functions, SOHCAHTOA, and then we have our cotangent and all of that as well. We've done all of those. There we have our tangent, secant, cotangent, and cosecant. The cast rule is one that we didn't really go over, but it's a good one to remember. The cast rule to determine when a trig function is positive or negative. If you think about it this way, starting at the bottom, cast, cosine is positive in this quadrant. All are positive in the first quadrant. The sine is positive in the second quadrant, and tangent is positive in the last quadrant, or the third quadrant. But if you start here in the fourth quadrant and just go cast, C-A-S-T, then you'll remember which is positive where. Everything's positive here, sine positive in this quadrant, and tangent positive here. The only one that's positive in this quadrant is the cosine. Okay, we have this chart already because we copied it down at the beginning of the year when we were on chapter 0. A lot of these problems I'm going to kind of brush over because we have done them. So that's basically a lot of what we had looked at so far. Now we're going to look at periodicity and the graphs of trig functions. So when an angle measure theta and an angle measure of theta plus 2 pi are in standard position, then their terminal rays coincide. Therefore, the angles have the same trig function values. So we've kind of done this as well. Here we have the cosine of theta plus 2 pi is the cosine of theta. I start over again. Same thing with the secant, tangent, cotangent, sine, and cosecant. A periodic function. Periodic function, f of x, is periodic if there's a positive number p such that for f of x plus p, it's equal to f of x. So if I pick the whole thing up and move it over a certain amount, it looks exactly the same. The smallest such value for p is the period of f. So if I'm looking at my sine function here, if I take this part of the sine function, I'm going to clone this, I'm going to make this one semi-transparent, I think. There we go. So you can see this, that if I set this right on top here, it's exactly the same. If I'm looking at my sine function, at 0, it's 0. At pi over 2, it's 1. At pi, it's 0. And at 3 pi over 2, it's -1. At 2 pi, it's back to 0. But basically, if I take this function, and if I'm starting at negative pi, and I move my negative pi over 2 over to 3 pi over 2, you're going to notice it lines up perfectly with 3 pi over 2. And that's simply because this is a periodic function. So that every time I am going through a cycle of 2 pi, I'm starting the whole thing over again. It would continue also like that if I set it here, taking the negative pi over 2 all the way over to 3 pi over 2. See how my pink line is lining up? And it starts over again and runs through that same pattern. It's going to do that forever. So my period of this function is 2 pi because it's a difference from 3 pi over 2 plus minus a negative pi over 2, or this distance pi over 2 plus 3 pi over 2 gives me 2 pi. It also works if I just started at 0 and went from 0 to 2 pi. Starting at 0, it goes up and then back down and ends at 0. My next cycle from 2 pi on is going to go from 0 back up to the same point that this was. So that's what makes it a period of 2 pi. That's how long it goes before it starts over. My range in this case is -1 to 1 because my lowest number is -1 and my highest number is 1. The domain is -infinity to infinity because for every x value there is a y going on forever. If we look at the cosine function is very similar. Clone it, set my transparency. If I take my negative pi and move it over to pi, you'll notice that my cycle starts over again. I'm lining up perfectly with it. And that's because it also runs on a sequence or on a period of 2 pi. So every 2 pi it starts over again. Again, starting at 0, when x is 0, y is 1. It then drops down, comes back up, and it's at 1 again at 2 pi. If I extend out past this, it's going to drop down again to 0, back down to -1. So it's going to run this same pattern of repeating. That means that my period is 2 pi for this as well. Range is -1 to 1. Domain goes from -infinity to infinity because there's always a point y if I put an x in. So cosine is very similar to the sine. That takes us to the tangent. When I look at the tangent, you'll notice that everywhere that there's a pink line, I don't have an answer because it's an asymptote. And that's at -pi/2, -3pi/2, pi/2, 3pi/2. It's going to extend out to 5pi/2 as well, and 7pi/2. It just keeps going up by 2pi/2. So my domain tells me that x cannot be equal to positive or negative pi/2, positive or -3pi/2, and extending out to positive and -5pi/2, 7pi/2, 9pi/2, 11pi/2, going up by 2 on our numerator each time. Our range in this case goes from -infinity to infinity because this keeps dropping down further and further as I get closer to -3pi/2 and as I get closer to -pi/2. And in this case, our period is pi. Because if I was to take pi/2 to 3pi/2, that distance is pi. 3pi/2 minus pi/2, that gives me 2pi/2. Cross out the 2's. 2pi/2. 2 divided by 2 just gives me 1, so it's 1 pi. If I look at the cotangent, cotangent is almost exactly the same, except it's flipped the opposite direction. Additionally, my domain switches. So for the cotangent, oh man, we're going to have a nor'easter set to blast eastern U.S. So here, with the cotangent, my asymptotes aren't at the same spots. They're not at -pi/2 and -3pi/2. You're going to find that your asymptotes are at 0, -pi, pi, and 2 pi. So my domain cannot be equal to 0, -pi, or positive pi, -2 pi, or positive 2 pi, and this one goes up by pi each time. My period is pi, and my range is from -infinity to infinity. I may have forgotten the, yes I did. With the cosine is the secant, and you'll notice that, remember that the secant is 1 over the cosine. And so when I look at this, my domain is going to be the same areas. It won't work at negative and positive pi/2, and negative and positive 3 pi over 2. My range is different because it's y is less than or equal to negative 1 and y greater than or equal to 1. And then my period is still 2 pi. While we're at it, we might as well go back to the last one and look at my cosecant. Cosecant, you'll remember, relates to sine. The cosecant is 1 over sine. Our period for the cosecant is 2 pi as well. The range is y is less than or equal to negative 1 and y greater than or equal to 1. And my domain is the same as sine was. All right, well, that is basically it for today. We are going to move on tomorrow and start looking at some of these symmetries, Pythagorean identities, which we've seen some of these already. And I will give you a list of your identities. I think you have it already, but I'll make sure that it's still on the page. And then we're going to start looking at shifting these graphs and doing transformations to it as well. All right, have a good day. Hope it doesn't snow too much.